this lesson is an extension of the gas laws that we went over the summer. And the first thing that I'm going to talk about is the kinetic molecular theory of gases. And there are 5 different postulates of the kinetic molecular theory of gases. And it helps us in understanding how gases interact with one another. The first one is that gases consist of large numbers of molecules, and they're continuously moving. So they're bouncing off each other, they're bouncing off walls. The next is that if you take all of those molecules of gas and you compress them, the combined volume of all of those molecules, their volume is going to be negligible relative to the total volume in which the gas is contained. So we're going to ignore the volume that the gas molecules actually take up. The third is that the attractive and repulsive forces between gas molecules are negligible. So we're assuming that they don't actually attract each other, they don't repel one another, but they do. They do in fact repel and attract one another, and we'll look at that when we're comparing ideal gases, which we're going to assume in this lesson, versus real gases. The fourth is that when molecules collide with one another, their energy is going to be transferred, so from one to the other. And as long as the temperature remains constant, then the average kinetic energy of the molecules is not going to change over time. And so that's one key relationship that we're going to look at further in just a second, that the average kinetic energy is proportional to the temperature. And the fifth and final postulate is that the average kinetic energy is proportional to the absolute temperature, what I just said for number 4. And so at any given temperature, the molecules are going to have a certain average kinetic energy. So that doesn't mean that all of the molecules are going to have the same kinetic energy. Some are going to have higher kinetic energy, some are going to have lower, but the average will stay the same at a given temperature. So the average kinetic energy, just to re-emphasize this, is proportional to temperature. Therefore, if you have 2 gases at the same temperature, they're going to have the same average kinetic energy. As temperature doubles, then, the average kinetic energy is also going to double. And so, as I just said in the previous slide, by saying average, we're acknowledging that some of the molecules are going to be moving more quickly than the average kinetic energy, while others will be moving more slowly. And so to represent this, if you look, the first thing I want you to notice is the difference in temperatures, 100 Kelvin, 300 Kelvin, 500 Kelvin. Notice that the velocity of these molecules, if they're at 500 Kelvin, on average, the velocity is going to be higher the higher the temperature is. Also notice that while the average might be one specific value, there's a large range of velocities and kinetic energies that the gas molecules can assume. Also notice that that range is much greater when the molecules are at 500 Kelvin versus when they're at 100 Kelvin. So if molecules are at a higher temperature, the range of velocities they can assume are going to be much greater than if they're just at 100 Kelvin. And this diagram is called the Maxwell-Boltzmann diagram. Now look at this second diagram. It shows velocity versus number of atoms. So notice xenon, argon, helium, we're going to assume that they're at the same temperature, so they should have the same kinetic energy. Notice that their velocities are very different, and that's because the formula for kinetic energy is 1/2 mv squared, m being mass. So the higher the mass of an atom, the slower its velocity is going to be. So while they might have the same kinetic energy, their velocities will be different. So the heavier an atom, the lower its velocity is going to be. The lighter an atom, the faster its velocity is going to be.
So now that I've talked about how gases interact with one another and some assumptions we can make using the kinetic molecular theory, I'm going to go back and talk about some of the gas laws we looked at first year in chemistry. So these laws should look familiar. The first one is Boyle's law. Now you don't have to memorize the name, but you do have to remember the relationship between these variables. So for example, in Boyle's law, it tells us that pressure and volume are inversely related, meaning if I decrease the volume, then the pressure is going to increase, or if I increase pressure, volume will decrease. They are inversely related. And keep in mind, we're assuming that we're going to keep temperature the same. Okay? For Charles's law, it's telling us that volume and temperature are directly related, meaning if you increase the volume, then the temperature will increase, or if you increase the temperature, volume will increase. Gay-Lussac's law is the exact same, but for pressure and temperature, they are directly related. Keep in mind, though, that for each of those three gas laws, you're holding one of the variables constant. So for example, Boyle's law, you're keeping temperature constant, Charles' law, pressure constant, and Gay-Lussac's law, volume is constant. Well, what if all three are changing? That would be the combined gas law. So that takes all three of those laws and combines them together. Okay, so let's look at some questions you might see in order to apply these gas laws. So for the first example, it says if the temperature were doubled and the pressure were held constant, how would that affect the volume? So here I'm using Charles's law. So if the temperature is doubled, remember temperature and volume are directly related. So if the temperature is doubled, the volume will also double. Okay? And let's talk about why exactly. Okay? Well, if you increase the temperature, keep in mind that the molecules are going to be moving around more quickly. They're going to have a higher kinetic energy. And therefore, they're going to collide with the walls of the container more frequently and with more force. So assuming that the pressure is staying the same, the only way to deal with those additional collisions is for the volume itself to increase. And so the volume of the container would increase. Now, if the volume couldn't increase, then the pressure would have to increase, and we'd have a Gay-Lussac situation in which temperature increases causes the pressure to increase, which again makes sense because the molecules are colliding more frequently and with more force. Well, what if I have two different things changing? What if my temperature is doubled and my pressure is also doubled? Well, if you look at your combined gas law, if your pressure is doubled and your temperature is doubled, those variables actually cancel each other out. And so that will actually have no effect on the volume at all. Okay? So while you will rarely actually use these formulas, you need them in your back pocket. If I ask you, hey, if this happens to a gas, right, if I'm increasing pressure, volume, or temperature, how would that affect another variable? You need to be able to relate them, knowing which ones are directly related and what is inversely related.
All right, so over the summer, we talked about different gas laws, combined gas law, Boyle's law, Gay-Lussac's law, and Charles' law. We're now going to talk about the last gas law, which is the ideal gas equation. So the ideal gas law is PV. The equation is PV equals nRT, P being pressure, V being volume, N being number of moles, and T being temperature. Now, R is your gas law constant, which will be given to you, and it's 0.0821 liter atmosphere Kelvin mole. And so the reason why these units are important, the liters tell you that your volume must be in liters. The units for volume must be liters. Your pressure must be in atmospheres. Your temperature must be Kelvin. And then moles must be moles. By using the ideal gas law, we're assuming that the gases are acting ideally, specifically that they do not interact with one another, just like we had seen with the kinetic molecular theory. They're not attracted to each other and they don't repel each other. And then also that when we combine their volume, that volume is going to be much smaller than the volume the gas occupies, meaning that the molecules take up no space. Now, that's not actually the case, and we'll look at real versus ideal gases in just a second. Real gases versus ideal gases. Molecules in an ideal gas are going to be in constant random motion, and therefore they're going to be spread really far apart, meaning that they're not going to be super attracted to each other. So how can we minimize the attraction they would feel? Well, we want them moving as quickly as possible, meaning we want a high temperature, and we want them as far apart from one another as possible, which means low pressure. So if you have high temperature and low pressure, under those conditions, gases will act as ideally as is possible. Now, when these conditions are not met, you're going to have a real gas. And if you use the ideal gas equation, when you have a real gas, you're going to end up with some errors. And so we're going to be dealing with real gases in labs, and so we're just going to have to accept there is going to be some error because we do not have ideal gases.
So if a gas is acting not ideally, okay, there are two different ways that they can act not ideally. The first one, and the assumption that we made before, was that they are not attracted to each other. Well, what if they are? What if they act like real gases that are actually attracted to each other? How would that affect the pressure? Well, if gases are going to be attracted to each other, right, if you think about it, they're going to be colliding with the container less frequently and with less force. And that's because instead of bouncing off of each other easily, and therefore just colliding with the sides of the container much more frequently, they're going to be attracted to each other. And so therefore, the pressure we would measure if they are actually attracted to each other, the measured pressure or the pressure we would actually get is going to be lower than what we would predict with the ideal gas law. And that's because the gases which are attracted to each other exert less force on the sides of the container. Okay? So that would cause the pressure that we actually measure in a lab to be less than what we would expect using the ideal gas law. So that's one way that gases can act non-ideally. What if gases actually take up volume? We're assuming when we have an ideal gas, the gases don't take up volume. Well, they actually do. So if you think about it, if all of these gases, which we assumed don't take up volume, they do take up space, that would cause the pressure to increase because all of a sudden you have these molecules that are taking up space, causing the pressure to increase, right? We assume you can basically ignore these particles of gas, and now all of a sudden we're saying you can't ignore them. They're taking up space. They therefore would exert a pressure, a greater pressure in that container, and therefore the pressure overall is going to be higher than what we would expect with the ideal gas law. Okay? So long story short, we assume that gases act ideally. They don't. Two ways that they don't act ideally. One, they're attracted to each other, which would cause our measured pressure to be lower than what we would expect. They can also take up volume, which would have the opposite effect, which would cause them to have a higher pressure than what we would expect using the ideal gas law. Okay, so just knowing how each of those deviations from ideality would affect the pressure that we would measure.
And finally, molecules are more likely to deviate when their intermolecular forces are strong. So yes, you want low pressure, high temperature, but another thing that influences whether or not they're acting ideally is the strength of their intermolecular forces, meaning if you have two atoms that have London dispersion forces, you want the one that with the weakest London dispersion force, and that one would deviate the least from an ideal gas. Something with hydrogen bonding, if it's a gas, would deviate the most from acting like an ideal gas, while something with London dispersion forces that's really, really small would deviate the least. So we're just going to be looking at a problem in order to make sure you understand this. So if it tells me I have 12.8 grams of aluminum and it reacts with hydrochloric acid, HCl, this is asking me how many liters of H2 would be formed at 715 millimeters of mercury and 19 degrees Celsius. So ultimately, what it's asking me to do is say, okay, I have 12.8 grams of aluminum. How many liters of H2 would be formed? The issue here is you've actually learned how to do this. The problem in this problem is that you're not at standard temperature and pressure. So you can't use the relationship between liters and moles that we learned, which is that 22.4 liters equals 1 mole. So instead, since you have a pressure and a temperature that are not standard temperatures and pressures, you're going to be having to use your ideal gas law. But in order to use my ideal gas law, which ultimately what I'm going to want to do is figure out the moles of H2 and then be able to apply that to my PV equals nRT equation, I have to figure out first the reaction between aluminum and hydrochloric acid and then be able to do the stoichiometry to convert between grams of aluminum and get myself into moles of hydrogen gas. So I first have to write out the reaction. So I know aluminum reacts with hydrochloric acid and it's going to produce, remember this is a single replacement reaction, so aluminum is going to go in and it's going to kick out the hydrogen because the hydrogen has a positive charge. So Al and Cl are going to combine together. Aluminum has a +3 charge, chlorine has a -1 charge, so that's going to become AlCl3 and hydrogen gas. Now the issue is, if you notice, I'm going to want 3 Cl's and 2 H's based on what I have in my products. The only thing they have in common is 6, so I'm going to put a 6 in front of HCl to balance that out. I'm going to put a 2 in front of AlCl3 in order to get those 6 chlorines. I now need a 3 in front of H2 in order to get 6 hydrogens. And finally, I'm going to put a 2 in front of aluminum, so I have 2 aluminums on my reactant and product side. Now that I'm balanced, I can do the stoichiometry to figure out how many moles of hydrogen gas I have. So I'm going to start with 12.8 grams of aluminum. I'm going to convert that first into moles of aluminum, because in order to go from terms of one reactant into terms of a product, I've got to use my mole to mole ratio. And in order to do that, I've got to be in moles of aluminum. So I'm going to put grams of aluminum on bottom, moles of aluminum on top. I have 1 mole for every 26.982 grams of aluminum, since that's the molar mass of aluminum. I'm now in moles of aluminum. I'm going to get into moles of hydrogen. So I'm going to put moles of aluminum on bottom, moles of hydrogen up top, and that ratio is based on the coefficients, so it's going to be 3 to 2. And now I can figure out my moles of hydrogen, because those are the units I'm in. So I'm going to take 12.8, I'm going to divide by 26.982, and then I'm going to multiply that by 3, which is the moles of hydrogen, and divide that by 2. Okay? And so that equals 0.71159 moles of hydrogen gas. So now I have my moles of hydrogen gas, I know the pressure of my hydrogen gas, and I know the temperature of my hydrogen gas. And so what I can do is now use PV equals nRT and solve for the liters of hydrogen. The only issue is because I have 715 millimeters of mercury, I first have to convert that. I'm going to take that, put atmospheres on top, millimeters of mercury on bottom. When I divide, I get 0.94079 atmospheres, and now I can use that pressure in my ideal gas law. So it's going to be 0.94079 times my volume. Well, I don't know what that is, so it's going to stay as V. That equals my moles that I just solved for, 0.71159, times my R, 0.0821, times my temperature. Remember, temperature, I just need to take 19 degrees Celsius and add 273 to that. Okay, and there we go. So I'm going to take what I have on my right-hand side, multiply them all across. Then I'm going to divide by 0.94079, and that gives me my volume, which is 18.1 liters.
So another situation that we could be in is, rather than being, for example, in the problem you just saw, at a pressure of 715 millimeters of mercury and 19 degrees Celsius, you could be at standard temperature and pressure. And so that's going to change the problem. It's actually going to make it easier. And the reason why it makes it easier is it lets us use a relationship that we haven't quite talked about. So let's look at the relationships with regards to moles that we have talked about. So first of all, we know that 1 mole of a substance equals the molar mass of that substance in grams. So for example, if I have 1 mole of oxygen, O2, I know I have 32 grams of oxygen. And that's why the unit for molar mass is grams per mole, because there are that many grams for every 1 mole. Another relationship that we know is Avogadro's number. So we know, for example, if I tell you, hey, I have 1 mole of nitrogen, you know I have 6.02 or 6.022 times 10 to the 23rd particles. That could be, so in that case, that would be atoms, but it could be atoms, it could be molecules or formula units. So if I have 1 mole of carbon dioxide, I would have 6.022 times 10 to the 23rd molecules of carbon dioxide. Now there's one other relationship that I'm now going to introduce, and that only occurs for gases, and make sure you know it's just gases. It does not apply to solids, liquids, or aqueous solutions. For gases that are at standard temperature and pressure, and remember, standard temperature and pressure is 1 atmosphere and 0 degrees Celsius. So the example problem we just did would not work because I'm not at STP. But if I am at STP, then I know that 1 mole of that gas has a volume of 22.4 liters. So it could be 1 mole of oxygen, it could be 1 mole of carbon dioxide, it could be 1 mole of nitrogen, it could be 1 mole of fluorine. It doesn't matter the identity of the gas. If I have 1 mole of it and I'm at standard temperature and pressure, so a specific pressure, a specific temperature, every gas will have a volume, ideally, of 22.4 liters. So the reason why I introduced this is because now, instead of having to use our ideal gas law, PV equals nRT, what that allows me to do is simply to use this volume, 22.4, as a conversion factor, so you no longer have to use PV equals nRT.
So let me show you what it would look like if I were at standard temperature and pressure, because for some of the problems I'll give you, you'll stay at STP, so it'll be a really nice, easy problem. So the setup at the beginning is going to be the same. Notice it states in the problem I'm at STP, so this is the only time you can do this, is if you're at STP. So you're going to go from 12.8 grams of aluminum, put grams of aluminum on bottom, moles of aluminum up top, okay? 1 and 26.982. Now I'm in moles of aluminum, just like the problem before. I'm going to get into moles of hydrogen. So moles of aluminum on bottom, moles of hydrogen up top, put a 3 and a 2. At this point, that was when I had to plug in my moles of hydrogen, whatever you got from this, into PV equals nRT because I was not at STP. But since I am at STP for this problem, what I can do is put moles of hydrogen on bottom, liters of hydrogen up top, and just say 22.4 liters equals 1 mole. So this problem is a lot easier because I don't actually have to plug it into the ideal gas law. And what I get for that is 15.9 liters. So the main thing for you to know is if I'm not at STP, I have to use the ideal gas law in order to figure out volume or whatever it's asking for. If I am at STP, I can simply use the fact that 22.4 liters equals 1 mole when I'm at STP. And what we're going to do now is we're going to use your ideal gas law and learn how to determine the molar mass of a gas. All right, so in this problem, it asks what's the molar mass in grams per mole of a gas if a 3.16 gram sample of gas at 0.750 atmospheres and 45 degrees Celsius occupies a volume of 2.05 liters. So this problem might seem super complex until you realize you're going to be having two different problems. The first problem you're going to do is you're going to be using the ideal gas law in order to solve for moles. So you're going to use your pressure, your temperature, and your volume to solve for moles. Once you know your moles, in order to get into molar mass, which by the way, the units are grams per mole or grams divided by moles, all you have to do is take your mass, which was the 3.16, divided by the number of moles that are involved, and that'll give you your molar mass. So let's actually do the problem. So I'm going to use PV equals nRT. I have my pressure already in atmospheres. I have my volume already in liters. I'm solving for N, my number of moles. I know my R is 0.0821, and my temperature right now is in Celsius, so I need to convert that into Kelvin by simply adding 273. So I plug in all of my values. Okay? I'm going to take 0.750, multiply it by 2.05. Then I'm going to divide whatever I get for that product by 0.0821, and then I'm going to divide that by 318. And what you get is your number of moles, which is 0.05889 moles. Now that I have my number of moles and I have my mass, you can determine your molar mass. All you have to do is take your mass, 3.16, divide it by 0.05889. That will give me grams per mole. And so what I end up getting for my molar mass is 53.7 grams per mole once I take into account significant figures. Okay, so the only thing that I've added to this problem, the only reason why this is slightly different from just an ideal gas problem, is the fact that I'm now asking you to take your moles and apply it specifically in order to determine your molar mass. And in order to do that, all you have to do is take your mass, divide by the moles that you calculated, and there's your molar mass.
So in addition to using the ideal gas law in order to determine molar mass, we can also use ideal gas law and density in order to determine the molar mass. So if we look at this question, it says, what is the molar mass of a gas with a density of 3.50 grams per liter at a temperature of 345 Kelvin and a pressure of 0.950 atmospheres? So the hardest part about this problem, ultimately, I'm trying to get into grams per mole, which is my molar mass. And if you notice here, I tell you the density, 3.50 grams per liter. And at first you might be freaking out about those units, but all that is telling you is actually that you have 3.50 grams in 1 liter. So 3.50 grams of that gas has a volume of 1 liter. So what I'm going to do is I'm going to use my ideal gas law, PV equals nRT, and I'm going to assume that the volume I'm using is 1 liter. And I'm going to plug in all of the values that I know in order to solve for moles. Okay? So to do that, I know my pressure is 0.950. I know my volume now is 1 liter. Okay? I'm going to be solving for N. I know my R is 0.0821, and I know my temperature is 345 Kelvin. So now I can solve for my number of moles, which is 0.0335 moles. Now another way of saying that is that I have 0.0335 moles in 1 liter, right? Because my volume is 1 liter. Or I could say that's 0.0335 moles per liter. So if you notice, I have 3.50 grams per liter, and I have 0.0335 moles per liter. So if you think about it, all you need to do to get into grams per mole, which is what I'm trying to do, get into molar mass, is I need to divide 3.50 by 0.0335 moles. Notice the liters will cancel and my final units will just be grams per mole. And so the answer I get for my molar mass here is 104.35 grams per mole. So you can use the ideal gas law in order to determine molar mass if you're given the mass or if you're given the density.
So I'm going to go through, now that we've talked about everything regarding gases and reviewed everything, I want to go back to some basics. Okay? So we assume with gases that they don't interact with one another, and that is going to allow us to make a couple of assumptions. So these are things that you should feel comfortable doing because gases don't attract one another. An assumption we're making that isn't true, but we're going to make it. So here's the first assumption. If you have more than one gas in a mixture, you can add up the total number of moles of that gas and then use it in your ideal gas law, right? So if you have, for example, 3 moles of N2, 2 moles of H2, and 1 mole of O2, and I say, hey, what is the total volume of that solution there, of that mixture? What you can do is simply use the ideal gas law, plug in all your values, and for the number of moles, simply add up all of the moles of gas. So that would be a total of 6 moles of gas in your ideal gas law. Keep in mind, pressure is 1, your total number of moles when you add them together is 6, and your temperature is 273. If gases actually interacted with one another, remember what I talked about with gases not acting ideally, that would actually mess with the pressure and the volume, etc. But we're going to assume they're not attracted to each other at all. And so thankfully, we can just add up the total number of moles. Well, if we can add up the total number of moles, we can also just add up the pressures. And so that is actually called Dalton's law of partial pressures. So here's an example. If I have oxygen, carbon dioxide, and nitrogen, and they have partial pressures of 0.5 atmospheres, 0.25, and 1.10 atmospheres respectively, what would the total pressure be? And so just like with the number of moles, I can just add up the partial pressures. So the total pressure would be 0.85 atmospheres. Again, if gases are not acting ideally, I can't make these assumptions, but I can because we assume they act ideally, which we're thankful for. The third assumption I can make, okay, I can determine the pressure. I can determine how the pressure changes by just looking at a chemical reaction. It's really cool. So let's look at this. Okay. I have 4 moles of oxygen gas reacting with 8 moles of nitrogen monoxide gas to produce 8 moles of nitrogen dioxide gas. Okay. What would happen to the pressure? Okay. Well, if you look at this, because I'm assuming the gases aren't interacting with one another, I can simply say, hey, I've got 12 moles of gas on my reactant side, and I've got 8 moles of gas on my product side. Which means, since I'm going from 12 to 8, my pressure is going to decrease. It's as easy as that. So it's really nice because you can look at a reaction and say, okay, how many moles of gas do I have on the reactant side? How many moles on the product side? And therefore, is my pressure increasing or decreasing? If you decrease your number of moles, the pressure is going to decrease. If you increase the number of moles of gas, your pressure is going to increase. And that's it. So I understand this is a lot of information. We've gone from your kinetic molecular theory all the way through your gas laws and your ideal gas law. I would strongly recommend, even though this is technically a review, I would strongly recommend going back, rewatching the video, and making sure you really understand what's going on.